Hello and welcome to this video for Chemistry 30 in the Organic Chemistry unit. In this unit, we're going to start learning how to name organic molecules. The last video talked about what organic molecules are, as well as how to identify different isomers of them. Well, in this video, we're going to look at not every single organic molecule that you see on this page, but we are going to start by looking at alkanes and cycloalkanes. So the organic compounds in Chem 30 that we're going to be focusing on naming are all listed here. There's several of them, okay? And as you can see, there's different generic formulas for how many C's and H's are in the compound, as well as any other elements. There's also the different ways that we're going to be naming them, some examples, and there's a couple of different rules depending on the type of compound you have for identifying the number of carbons in the parent group or how to number the carbons in the parent group. Okay, so like I said, this seems like a lot, but we'll take a few lessons to go over it. And in this video, we're going to start with just the simple alkanes and cycloalkanes, which are very similar. If you look at their name, their suffix of the name end in -ane or begins with cyclo and ends with -ane. So for example, 4 carbons here in a chain is called butane. 4 carbons in a ring structure here is called cyclobutane. Okay, so let's talk about, first of all, we're going to get into the different prefixes that we use. So notice here how my prefix in front of the -ane was bute. Where does bute come from? Okay, and bute comes from the fact that we have 4 carbons, but I thought the prefix for 4 was tetra, right? Back in Chem 20 Science 10, we learned that 4 is tetra. Well, sometimes we use tetra and sometimes we use butes, and we're going to talk about how you know when to use them. Okay, but notice here in some of my compounds, like my alcohol, I have something called an OH. We call that a hydroxyl functional group. R just means that this can be any type of carbon chain or ring structure, but if there's an OH, an oxygen and hydrogen bonded to it, it's called a hydroxyl functional group. The functional group is something that makes it that specific compound. Whereas when you have the COO in the compound, it makes something called a carboxyl functional group. Okay? When you have a halogen in your compound, they're called a halide functional group. Branches can also be considered functional groups. So why I'm talking about functional groups is because when you're talking about how many functional groups you have, if you have multiples of the same functional group, then you are going to use the original prefixes that we used back in Science 10 Chem 20. You're going to use di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay, so again, the functional group can be like I showed you on that last slide. If I go back here, it can be carboxyl functional groups, which are COOH. They can be hydroxyl functional groups, halides. And what's not on here are branches, okay? And a branch is when you have a carbon coming out of the middle of a parent chain or ring structure. A branch is made of carbons, and they make something that we call an alkyl functional group, okay? So when you have an alkyl functional group, multiples of the same, then again, we can go back and use these prefixes, okay? This will all make more sense when we get into some examples, all right? Now, the regular prefixes that we use for the rest of naming organic molecules are as follows. 1 is meth. 2 is, sorry, I have some sound effects here. I just have to turn my volume down. 2 is eth. 3 is prop, 4 is bute, 5, 6, 7, 8, 9, 10 are kind of the same. They just don't have an A at the ending, so it's not penta, it's pent. And 6 is hex, hept, oct, non, dec for the rest. Okay? So this represents how many carbons you have, either in the chain, the ring structure, or the branch that you have. Okay? These are the prefixes that we're going to use from now on. So you do need to memorize these. Meth, eth, prop, bute, pent, hex, hept, oct, non, dec. And we're going to go as high as 10. Okay, so you do need to memorize these. Now, the first compound we're going to focus on are called alkanes. Now, alkanes are compounds that have only single bonds. When a compound has only single bonds, it's considered a saturated compound. You do need to be able to categorize your organic molecules as either saturated or unsaturated. Alkanes are saturated, okay? They have the full number of single bonds that they can have. They're going to have a total, remember, like we looked at in the last unit, 4 bonds around each carbon, okay? Now, when you're looking at the formula of a compound, how can you tell if it's an alkane? Well, if the number of hydrogens compared to the number of carbons is double plus 2, you have an alkane, okay? Fully saturated hydrocarbon. They can exist as a continuous chain. They can have branches, and they can also make, like we looked at there, ring structures. But when they make ring structures, they're kind of like a subgroup of alkanes. They're called cycloalkanes. Okay, now it is important to note, so when we get into cycloalkanes, we'll look at this. They do have a little bit of a different formula than a regular alkane. Alkane number of hydrogens was double the carbons plus 2. A cycloalkane is just double the number of carbons for hydrogens, all right? Because the end carbons have to each lose a hydrogen so that they can bond together, making the ring structure, the cyclic structure. So what that means, remember we looked at isomers yesterday. Isomers are when you have two compounds that have the same carbons and hydrogens, but a different structure, giving them a different name. So an alkane and a cycloalkane can never be isomers of each other because they would never have the same hydrogens when they have the same number of carbons. So what are some properties? You do also need to know the properties of all of your organic molecules. So these are all nonpolar. They are tetrahedral around the carbon. Tetrahedral, remember, if all the terminal atoms are the same, they will cancel and be nonpolar, right? The only elements in these compounds are hydrogen and carbon. So all of the terminal atoms are the hydrogens. As long as the terminal atoms are the same around your carbon as a tetrahedral shape, or actually any of the shapes that the carbon can make, tetrahedral, trigonal planar, or linear. All of those, the bond dipoles will cancel as long as the terminal atoms are the same. So if they're all hydrogens, they are the same, and therefore these molecules are nonpolar. So they will only have London dispersion forces. Whereas water, as we know, has London dispersion, dipole-dipole, and hydrogen bonding. So if they do not have the same forces, they are not soluble. They can be solid, liquid, or gas in states depending on how many carbon atoms you have in the molecule. So for example, if I have 1 carbon in my molecule, the simplest alkane I can have, that would be carbon with 4 hydrogens. That is methane, and that is a gas. Whereas when I get up to something like octane, which has 8 carbons and 8 hydrogens, that is a liquid. And then if I get even more carbons, like C25H52, that is paraffin wax, which is a solid. So the reason this is happening is because the more carbons you have, the more hydrogens you have, so the more elements you have in total, which is going to give you more electrons, and more electrons means a greater chance that they become polar, temporarily polar. And remember, that's what London dispersion forces are, how often they become temporarily polar, or how polarizable they are. When there's more electrons, that happens more often. So stronger London dispersion forces equals a higher boiling point. Higher boiling point means they're going to have a state more likely of solid or liquid versus gas, for example. Okay? Now, the other thing that I've seen on the Alberta diploma is looking at how whether you have a chain, a straight chain, versus a branched chain. So this is 5 carbons in a continuous chain. If I put my 5 carbons, 4 of them in a chain, and 1 of the carbons as a branch, remember we looked at doing that yesterday with drawing isomers. These would be 2 isomers of C5H12. The chain that is a continuous chain versus the branched chain has more surface area, allowing another molecule to have more contact. Because remember, when we're talking about boiling points, we're talking about separating two molecules apart from each other. So this is another molecule of my C5H12 as a what we would call straight chain, okay? So when it's a straight chain, they can get closer to each other and have more interaction, making it harder to separate them. So the London dispersion forces are going to be stronger when they're a straight chain versus when they have branches. They can't get as close to each other and have as much overlap or direct surface area contact with each other. So higher London dispersion forces, again, is going to make it have a higher boiling point, okay? Now, the other thing that we're going to talk about with our organic molecules are reactivity and stability. So in order for something to be reactive, it has to be unstable. Well, because of the single bonds in our alkanes and that the fact that they are fully saturated means they're already stable. They have the maximum number of single bonds that they can have. When you have single bonds, they're stable, making the compound unreactive, okay? Double and triple bonds are less stable and they become more reactive, which we'll get into later when we talk about those type of compounds. So what are some uses? Natural gas. What is natural gas? Natural gas is methane. Well, using our prefix rule, meth means one. So this is one carbon with 4 hydrogens, because it has to be double the hydrogens plus double the carbons plus 2 to make the hydrogens. Barbecues use propane. So prop is the prefix there. That would be C3. And the number of H's you would have, again, is double the carbons plus 2, which would be 8. Lighter fluid is butane. Bute, that's C4H10. And gasoline is octane. So notice how they're all ending with the suffix ane because they're alkanes. And octane is C8H18. The prefix tells you how many. Now these are very simplified names. When you have just a continuous chain, there's no branches in your molecule. When we get into branches, it's going to be a little bit more complicated. Okay? So we are going to be following the IUPAC system name for the IUPAC system rules for naming organic molecules, which stands for the International Union of Pure and Applied Chemistry. Anytime we've been naming throughout Chem 20, Chem 30, Science 10, we've been following these rules. So these are always the same rules that we follow. So like I said, when you have a continuous chain, all you have to do is name the prefix, the suffix ane, and you're done. So I have 1, 2, 3, 4 carbons. It is just butane. Okay, very straightforward. Prefix for 4 is bute, and again, they all alkanes, which are single bonded compounds, all end in ane when they have just carbon and hydrogen. Okay. Now, and before actually I move on, just a reminder that there are a variety of different ways you can draw this or be given a diagram. Remember, if you're given a line diagram, this is what butane would look like. For line diagrams, every end of the line or every corner of the zigzag is another carbon. So that's 1, 2, 3, 4 carbons. In line diagrams, they don't show the hydrogens, they don't even show the carbons, they just show the bonds between the carbons, okay? So that's what butane would look like as a line diagram. Now, what about when we get into branches? So as I mentioned, branches are called alkyl functional groups, okay? And why you want to know that is, again, because the name of it tells you what the name is going to be as a branch. So when you have a 1 carbon in your branch, it is called a methyl branch. Okay, alkyl ends in YL, methyl ends in YL. 2 carbons would be called ethyl. 3 carbons would be called propyl. Okay, these are carbons as branches. All right. Now, let's say you have 3 carbons and you as a branch. So let's pretend whenever you have an organic compound, the longest continuous chain is the parent chain. So let's say that's my parent chain that has 5 carbons. And then let's say I have a propyl branch. I didn't give myself much space here. Let's say I have a propyl branch, which is 3 carbons in that branch. Okay, so when you're actually 1, 2, 3, 4, 5, 6. This is not possible. Let's pretend we have a 2 long carbon. I'll explain later why that's not possible. But anyway, so when it comes to figuring out what is the parent, what is the branch, the longest continuous chain, which doesn't have to be straight across. Usually it is, but it doesn't have to be. Okay, if I go straight across, I have 1, 2, 3, 4, 5 carbons, but I could also snake down. If I snake down, I have 1, 2, 3, 4, 5 carbons. It's the same thing. Okay, so you find either way, you're going to get the same answer, the longest continuous chain to be your parent, and then the other carbons that are coming off of the middle of the chain is a branch. So that is a branch that has 2 carbons in it. Okay, so a 2 carbon branch again is called an ethyl branch. So the actual name of this, because you're going to, again, first identify your longest chain as your parent. You're going to then number the longest chain so that the branch gets the lowest possible number. So either numbering from left to right or right to left, from one end to the other of the longest continuous chain. So if I number from left to right, my branch is on carbon 3. If I number from right to left, my branch is still on carbon 3. Okay, so at this point, it doesn't matter which way you number it. Then you're going to name the branches first, actually, in alphabetical order when you have multiples of them, including the number of the carbon where the branch is found. So for example, what this is again a 2 long carbon branch. So this is an ethyl branch, and it is on the 3rd carbon of my parent chain. So the name of this would be 3. Between every number and every letter we put a dash. So 3-ethyl. So that means again, on the 3rd carbon of the parent chain, there is a 2 long carbon branch called an ethyl branch. And then I name the parent, which is 5 carbons. So the parent would be called pentane. So the full name of this compound, one word, is 3-ethyl pentane. Okay? Now sometimes you can draw, and like I said, there's a variety of different ways you can draw these molecules. Okay? This is a complete diagram where I'm showing everything. I'm not showing the hydrogens, but I'm showing lines going to nothing, which means they're going to hydrogens in a complete diagram. Okay, so make sure you always have 4 lines around every carbon. I accidentally erased one of these lines. There's a line right there. Okay, you have 4 lines around every carbon. Now you can condense the formula. If I were to condense this, I would have CH3 for carbon 1, CH2 for carbon 2. Carbon 3 has just 1 hydrogen. And it has that ethane branch. Now, if I were if I were to condense that ethyl branch, I could condense it. I'm actually going to draw this down here so I have more space. CH3, CH2. Now, I could condense it into 1 carbon. This carbon here has 2 H's. And then this carbon here, which has 3 H's. Okay? And then if I finish the rest of the compound, carbon 4 has 2 H's, and then carbon 5 has 3 H's. Okay, so that's one condensed method of drawing it, but you could actually put these 2 carbons together and call this branch C2H5. There are 5 H's, 1, 2, 3, 4, 5. Okay. Now, kind of a shortcut, when you're trying to figure out how many hydrogens you have in a branch of any type of hydrocarbon, methyl is going to always be, as a condensed branch, CH3, okay? It's the carbon is bonded to another carbon, and then the rest of the 4 bonds are hydrogens. Ethyl condensed is C2H5. Propyl condensed is C3H5. CH7, okay? Very similar to the formula for the overall compound, but it's just double the number of hydrogens plus 1 because the other bond is of that carbon branch is bonded to the rest of the carbon parent, okay? Let's look at some more examples. So here I have my carb. Now notice here too how it's kind of drawn where you have partially condensed, partially complete diagram. You can do that. You can draw them however you want if the question doesn't state. Now the condensed ones don't have to be the branch. They could be, but they don't necessarily have to be. Okay? You're again starting with your parent as the longest continuous chain. So you're going to take a highlighter or a pencil and look at how far you can go without lifting your pen through the carbons. If I go straight across, that's 1, 2, 3, 4, 5 carbons. But I could also go down just to double check if that is any longer. 1, 2, 3, that's only 4 carbons. Okay? Or I check going down this direction. 1, 2, 3, that's only 4 carbons. So you try all the different paths and see where you can get the longest continuous chain, and it doesn't have to be straight across. Okay? In this case, the longest chain is straight across, 5 carbons, but it doesn't have to be. Okay? So always double check that. Now, what you have left, the other carbons of the compound are now branches, okay? And that has 1 carbon in it, so that is a methyl branch. Then your parent, again, you're going to number it so that your branch has the lowest number. So if I number it from left to right, my branch is on carbon 3. If I were to go from right to left, it would also be on carbon 3. So it doesn't matter which way I number it here. Now to name it, I again start with my branch. So on carbon 3 of the parent chain, dash, there is a methyl branch. And my parent is 5 carbons, which would be pentane. So 3-methyl pentane is the name of that molecule. Okay, next molecule, again starting with finding my parent chain. If I go straight across, I have 5 carbons. If I try bending down, I have 1, 2, 3. I also have 5 carbons. Okay, so it doesn't really matter if either way you go, you get the same. You can pick either one to be your parent. You're going to get the same answer. Try this way. 1, 2, 3, 4, 5. Same thing. I have 5 carbons in a chain. Okay, or I can go 1, 2, 3, 4, 5. Another 5 carbons in the chain. Okay, so you want to pick. Now here's the issue with this way. If I were to make this my parent, the problem is this would be a branch, and then that would be a branch off the branch. You can't have that, okay? You can't have a branch coming off the branch. So picking your parent at least needs to, I could make this my parent so that the branches don't have any branches on them, okay? Or you can go straight across, but I'm going to show you how if I bend down, I get the same name as if I go straight across because the number of carbons are still the same length, okay? So if I bend down like this, this becomes a branch and this becomes a branch, okay? This has 1 carbon in it, that has 2 carbons in it. Numbering my compounds, I need to number in this direction, 1, 2, 3, 4, 5, instead of starting at the bottom and going up, so that my branches are on carbon 2 and carbon 3. If I started at the bottom and went up, they would be on carbon 3 and carbon 4. We want the lower numbers, okay? Now when it comes to naming them, remember a 2 long carbon branch is called an ethyl branch. And a 1 long carbon branch is called a methyl branch. I have to name the branches alphabetically. So I'm going to start with the ethyl. E comes before M. Okay? So on carbon 3, I have an ethyl branch. So it's 3-ethyl. Between every letter and every number, there's a dash. Then I also, on carbon 2, have a methyl branch. So it's not just the ethyl branch, there's also a methyl branch. Okay? And then my parent has 5 carbons, so it is pentane. So it's 3-ethyl dash 2-methyl pentane. Now let me show you how this is the same name if I would have instead made my parents go straight across. If I made my parents go straight across, I still have, sorry, my pen sometimes likes to do its own thing. I still have 5 carbons, that's the longest continuous chain. I still have a methyl branch on carbon 2 and a 2 long carbon ethyl branch on carbon 3. Okay, so the name is still the same. That's why I said when you're naming it, if whichever way you find the longest parent chain, if there's multiple ways to get the longest parent chain where you don't have any branches on a branch, you can do either way and you're going to get the exact same name. Okay, so again, this would be called, on carbon 3, there is an ethyl branch. Alphabetically, that has to go first. Carbon 2, there is a methyl branch, and the parent is pentane. Okay? So start by finding your parents. The longest continuous chain doesn't have to be straight. Let's look at an example where we have 2 branches that are the same branch. Okay? So here, and if going straight across gives you the longest parent, that's usually what I do. I just go straight across, that's the longest parent. If I were to bend down and zigzag, I would get still the longest being 5 carbons. 1, 2, 3, 4, 5. Okay? I'm numbering it in this direction, again, because I want my branches to have the lowest possible number. I have a methyl branch and another methyl branch, 2 methyl branches. Okay? On carbon 2 and 3, numbering it from left to right to get the lowest number. Now, when I have 2 branches that are the same, these are both methyl branches, we actually can combine them together, okay, and use the prefix di. So I have 2 of the same branches. They're on carbon 2 and carbon 3, so this is how I name it, okay? It's 2, 3 dash dimethyl. So this means that there are 2 methyl branches. I have to have a number for wherever each methyl branch is, even if they're on the same carbons and I use the same number more than once. Okay, so 2, 3 dash dimethyl. All the parents we've done so far have been pentane, just to show you again. Just some examples where they're very similar, just changing the branches up a little bit. So this is 2, 3 dash dimethylpentane. Now, what if I were to ask you for the formula of this compound? Remember, the formula is the total carbons, not just in the parent. So I have 5, 6, 7 carbons. Now, using my formula, double plus 2 should be 16 hydrogens. Double check, go through and count and see how you have 16 hydrogens. There's 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens. Okay? So that is 2, 3 dash dimethylpentane. Now here's some to try. You can pause the video and take a try and see if you can name these, but I will also go through and show you what the name should be. Okay, so starting again by finding your longest continuous chain. I'm actually going to do that for all of them to start. Find my longest continuous chain. It doesn't have to always be straight across. Sometimes it bends down. Okay, so it takes a little bit of practice, trial and error, but you try going through all the different ways, the longest continuous chain. So where you can go through the maximum number of carbons without lifting your pen. Then the other carbons coming off the middle are branches. Branch, 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 branch. Okay, those are all my branches. Now I need to number my parent chain, which is the yellow one, the lowest branch numbers. So 1, 2, 3, 4, 5, 6. That's the best way to number that one, to get the branches on 2 and 4. This way, again, if I number in this direction, I get my branches on 2 and 4. If I go the other way, from the bottom up, they would be 4 and 5, or 3 and 4, sorry. 3 and 6, my gosh. Okay, this way, 1, 2, 3, 4, 5, 6, 7. And this way, 1, 2, 3, 4, 5. My pen is being very difficult today. 1, 2, 3, 4, 5. And it erased my parent there. Okay. So now to go through and name them. Notice how all of the branches in all of these compounds have just one carbon in them. So they're all methyl branches, okay? On the first one, we'll call this carbon 1, molecule 2, molecule 3, and molecule 4, okay? So for the first one, I have 2 of the same branches, 2 methyl branches, so I can combine them together. So it'll be 2, 4 dash dimethyl. Oh, my pen, why are you being so weird today? Dimethyl. I think if I hold the pen down too long, it does that. Pentane. Okay? The next one actually has the same name. Now, if it has the same name, is it an isomer? The answer is no. In order to be an, not pentane, hexane. In order to be an isomer, they have to have different names, yet having the same formula. These have the same names and the same formula. So they are not isomers. They are the same molecule, just drawn where one's bent and one's straight. You're not breaking any bonds, it's just moving around. Okay, so these are the same molecules, 2,4-dimethylhexane. The next one would be 2,4,6-trimethylheptane, because there's 7 carbons in that parent. And the last one, there's 4 methyl branches. 2, 2, 4, 4. That should be a 4. 2, 2, 4, 4. Tetramethyl. And now this parent is a pentane. Okay? So that is, again, even when you have, if you have 4 branches, you need a number for all of them, even if they're on the same carbons. So I write the 2 twice and the 4 twice. Okay? I think that all looks good. Hopefully there's no mistakes there. Let's look at drawing them now. So when you're asked to draw them, look at the end of the name to find the parent. And I always start with that. Okay? The end of the name has the parent. Then I add the branches, and remember to make sure that you have 4 bonds around every carbon, okay? So here, for example, my parent is propane, 3 carbons, and then on carbon 2, so if I make that carbon 2, I have a methyl branch and another methyl branch. There's 2 methyl branches. Now, sorry, I automatically do that, but let's say I drew it like that, okay? That would be wrong. If you're drawing a complete diagram, you're not showing the 4 bonds around every carbon in this diagram. you need to show at least the lines going to nothing, and we assume that means it's going to hydrogens. Now you can always draw the hydrogens too if you want. Hydrogen, hydrogen, hydrogen. It's just that it takes a really long time, and so kind of a shortcut for my students I say is as long as they draw the lines going to nothing, that means they're going to hydrogens. But that's really what it would look like with all the hydrogens, okay? Now that's the complete diagram. If the question doesn't tell you how to draw it, you can draw it however you want. Very commonly, I tend to draw in my answer key the complete diagram for the parent chain and then branches for, or condensed form, sorry, for the branches. So that's probably how you would see that molecule drawn in my answer key. But I could also condense the whole thing and make it CH3 to C to CH3 to CH3 to CH3, right? This is still my parent chain. The CH3s don't have to be the branches. They're just a condensed form of showing how many hydrogens are on the carbon, okay? Or line diagram. 1, 2, 3 carbons and a branch and a branch. So that's what a line diagram would look like for 2,2-dimethylpropane. Once you kind of get the hang of the line diagram, they're actually quicker and easier to draw. So these are all the variety of ways you can draw 2,2-dimethylpropane. Okay? Hexane. I'm going to just draw what you'll see in my answer key, which is the partially condensed, partially complete form, and then as well the line diagram just to show you how to do that. So hexane is the next parent. 1, 2, 3, 4, 5, 6 carbons, and I number it. 1, 2, 3, 4, 5, 6. On carbon 4, there's an ethyl branch. Doesn't matter if you go up or down to draw your ethyl branch. That is C2H5. On carbon 2 and 3, there are methyl branches. Di because there's 2 of them. One on carbon 2 and one on carbon 3. Again, it doesn't matter if you go up or down. You can go down, up, like it doesn't matter as long as they're on carbon 2 and 3. Okay? Finish off by putting your lines to hydrogens. Make sure you have 4 bonds around every carbon. Okay? Now the line diagram. 1, 2, 3, 4, 5, 6 hydrogens. On carbon 2, there's 1 carbon. On carbon 3, there's 1 carbon. On carbon 4, there's 2 carbons. So 1, 2. So that is how that one would look. Now, does it have to be 1, 2, 3, 4, 5, 6? This could have gone down. This could have gone up. This could have gone this way. Okay, it really doesn't matter. There's not just one way of drawing a line diagram. Just making sure that you understand, if I were to label this, these are my carbons. Okay, carbon, 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 carbon. All right, so there's not really one only way to draw line diagrams. Like, do you go up or down? Which way do you bend it? None of that matters. Okay. Just understanding that every corner, every end of the line is a carbon. For propyl octane, that one, my parent has 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. On carbon 4, I have a propyl branch. That is C3H. Double is 6 plus 1 would be 7, okay? Then I finish it off again with my hydrogens. Do not forget to do that. You will lose marks if you forget to have 4 lines around every carbon. There's a line there, you just can't see it, okay? Line diagram, 1, 2, 3, 4, 5, 6, 7, 8. And then on 1, 2, 3, 4, there's a propyl, 1, 2, 3, for example. Okay, again, let me try that again. 1, 2, 3. It doesn't have to be perfect. There's not, again, a specific way it has to be. Okay, 1, 2, 3, 4, 5. Yeah, that looks right. And then the last one, heptane. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. On carbon 3 and 5, there are ethyl branches. So I'm just going to go up with these because it really does not matter if you go up or down. Okay? Carbon 4 is a methyl branch. Just to save some space, I'll draw that one down. It just matters on which carbon it is, not if it's going up or down. Okay? And then line diagram, 1, 2, 3, 4, 5, 6, 7. And on carbon 3, there's an ethyl branch, 1, 2. On carbon 5, there's an ethyl branch, 1, 2. On carbon 4, there's a methyl branch. Okay? All right. Now, here is a sample diploma question. Which of the following line diagrams represents 2,3-dimethylpentane? So when I see a line diagram, I always take my pen, identify my carbons, and name it, and see which one matches. Okay? The first one, for example, there's only 4 carbons in the parent, so it's not even a pentane, it's a butane, so it can't be that one. This one has 5 carbons, but the branches, the methyl branches, are on 2 and 4. We want them on 2 and 3. Okay? This one here, 2, 1, 2, 3, 4, 5. My methyl branches are on 2 and 4. Hopefully D's right, because the other ones aren't. I do have, because I would actually number it this way to give my branches the lowest number, 2 and 3. 2,3-dimethylpentane. So D is the answer. Now, before we finish, we are going to also look at cycloalkanes in this lesson. What is a cycloalkane? It is where your parent is actually a ring structure. Okay? Remember we talked about how they have a slightly different generic formula. They only have double the number of carbons for their hydrogens. Okay? And when you draw them, they're usually drawn as a line diagram. And when you name them, you put the word cyclo in front of the parent name. Okay? So, again, this is every corner is a carbon. So there are 4 carbons all continuously bonded in a continuous cycle or ring structure. And so the name of that is cyclobutane. Okay? The next one has 1, 2, 3 carbons. That is cyclopropane. Okay? Now, if I were to draw these out as complete diagrams instead, this is what it would look like, just to show you what it would look like. Okay? Now, every corner or every carbon would need 2 hydrogens on it to make sure that everything has 4 hydrogens. So the formula for this would be C4H8. Okay, just double, not double plus 2. Cyclopropane would be 1, 2, 3. Again, every corner having 1, 2, 3, 4, 5, 6. So C3H6. Every carbon should always have 4 lines. So once you draw the carbons joined together, the leftover lines are going to hydrogens. Now, what do you do if you have branches? Because these all didn't have any branches, and you can have branches. Here's an example. When you have branches, you're going to start at one of the branches, and then go either clockwise or counterclockwise till you get the lowest number sequence. Okay? So, for example, I can start 1 at this methyl branch. Then I'm going to go in this direction to get the lowest number on my other branch, which is the ethyl branch. So my branch sequence at this point is 1 branch is on 1, 1 branch is on 3. Okay? If I try other ways, let's say I start 1 here, go in this direction, my branch sequence is 1 and 3. So if you can go multiple ways and you get the same branch sequence, it actually doesn't matter which one you choose. Okay? You will get slightly different names. So let's say I name it the purple way. On carbon 1 is my ethyl branch. I'm still naming my branches alphabetically. On carbon 3 is my methyl branch. And the parent is cyclo, don't forget the cyclopentane. okay? Now, some textbooks will say that this is the preferred method for numbering it, just because alphabetically the ethyl comes before the methyl, so why not make the ethyl the lower number? That's not a hard rule. I have also seen this very correctly being named instead 3-ethyl -1-methyl cyclopentane. Okay, either way is absolutely correct. So in my answer key, you can see both of these being mentioned. Just always remember to make sure the branches are in alphabetical order. Now, another thing I want to mention is the whole lowest sequence thing. If I were to have, so you're starting at one of the branches, going clockwise and counterclockwise, looking at all the different number sequences you get for your branches. If I go one way and get a 1, 8, and 9 on my branches, go another way and get 2, 3, and 4. The question is, which is the lowest number sequence? And a lot of students will mix this up. It's actually the first one, okay? Because what a number sequence means is you're comparing them one digit at a time. So you look at the first digit. If you have a 1 versus 2, the 1 is less. Doesn't matter what the other numbers are. 1 is less, okay? So you go with that one, all right? Okay, let's look at some more examples. Okay, I will go 1, 2, 3, 4, or the other way would have been 1, 2, 3, 4, same thing. 1, 2, 3, 4, 5, 6, and maybe pause this video, try these on your own, and see if you can number them in the proper way. Obviously, the first two are pretty straightforward. I have 1, 2 dash dimethyl cyclobutane. Pretty straightforward. The second one is 1, 1 dash diethyl. Those are ethyl branches. Cyclohexane. Okay, again, even if they're on the same carbon, you need to write the number more than once. One number for every branch. These again, right, are ethyl branches. They have 2 carbons in it. These are methyl branches. They have 1 carbon in it. The numbering of this one is a little trickier, and you want to, like I said, start at 1 somewhere and write down the sequence and try all the different ways, okay? So this is actually the correct way, where I have a branch on 1, 2, 4, and 6. 1, 2, 4, and 6. But let me just show you why that's the proper way. Let's say instead I start here. Make this 1, 2, 3, 4, 5, 6, 7, 8. Then my branches are 1, 2, 5, 7. 1, 2, 5, 7. 1, 2, 4 comes before 5, so it's the better sequence. Other ways I could try, let's start here. 1, 2, 3, 4, 5, 6, 7, 8. My branches are on 1, 3, 5, 6. 1, 3, 5, 6. So you try all the different ways. Remember, you compare them one digit at a time. Okay? So at first they all start with 1s, we look good. Then we look at the next number, 2, 2, oh, 3. Nope, that's not good. Then we look at the next number, 4 versus 5. Nope, not good. So that's why that first way of numbering, and it just kind of takes some practice and you kind of get an eye for it. 1, 2, 3, 4, 5, 6, 7, 8 is the best way to number it. Okay, now this is a big, long, crazy name, so I'm going to erase this to have some room for myself. I do need to name the branches alphabetically. Okay, I have an ethyl branch and an ethyl branch here. I have a methyl branch and I have a propyl branch. So alphabetically, the E's come first. So that is 4, 6 dash dimethyl. Ethyl, sorry. The di does not change the alphabetical order. It's the E that we're looking at, okay? So 4, 6 dash diethyl. L, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. So M comes next. That's my methyl branch on carbon 2. Then my propyl comes last. Oops, I'm just showing you the alphabetical order here. E, M, and then my propyl, P, on carbon 1. And this is a cycloalkane. And you do look funny, have 2 O's side by side there. Okay, so 4,6-diethyl, 2-methyl, 1-propyl cycloalkane. All right, that is the full name of that molecule. Name the branches alphabetically, but number the carbons on the parent ring structure so that the branches get the lowest number sequence. Let's draw some. 1,2-dimethyl cyclopropane is my parent. Cyclohexane is my parent. Cyclopentane is my parent. So you kind of get some practice with drawing shapes here. Here's cyclopropane. It doesn't look perfect, but that's fine. And I have methyl branches. You can make any corner that you want, carbon 1 and carbon 2. But I decided to make that 1, that 2, and that 3. Okay? Cyclohexane, that is a hexagon. On carbon 1, let's make this carbon 1. You can, like I said, make any corner that you want 1. I have 4 ethyls, 2 on carbon 1 and 2 on carbon 2. And then cyclopentane, that is a house looking structure. Okay, 1, 2, 3, 4, 5. On carbon 1, I actually have 2 methyl branches. On carbon 2, I have a methyl branch, and on carbon 3, I have a butyl branch. That's C4H double plus 2 plus 1, so it's 8, 9. Okay? Now, while we're here, let's look at writing the formulas for these, because that's still something you do need to know how to do. Let's say we are looking, we'll do the last one, okay? So I'm going to erase these little numbers, and I'm going to draw carbons in this diagram. So there is a carbon here, a carbon here, a carbon here, a carbon here, a carbon there. Okay? I'm going to draw the bonds again as lines and making sure I have 4 bonds around every carbon to figure out where my hydrogens are. I'll draw my hydrogens as blue. Okay? This, again, was carbon. I'll put the numbers in. 1, 2, 3, 4, 5. Carbon 1 already has 4 bonds, so it has no hydrogens. Carbon 2 has 3 bonds, so it needs 1 hydrogen. Carbon 3 has, again, 3 bonds, so it needs 1 hydrogen. Carbon 4 only has 2 bonds, so it needs 2 hydrogens. And carbon 5, again, only has 2 bonds, so it needs 2 hydrogens, right? The hydrogens fill up the maximum of 4 bonds around every carbon. So the formula for this would be C, don't forget the branches, so 5, 6, 7, 8, 9, 10, 11, 12, C12. Following my generic rule formula, it should be double the hydrogens, but count and make sure that's what you have. You have 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay? So always double check when you're writing the formula. Make sure you can identify how many hydrogens you have compared to carbons. Okay? And that, I believe, is it for this first lesson, where we have looked at naming alkanes and cycloalkanes. Thank you very much for watching this video.